All right, welcome to part 2 of our Module 2 lecture series. In this part, we are going to talk about the normal curve, or the bell-shaped distribution. So, in the previous lecture, I showed you guys a representation, right, of a bar graph, or if we had a histogram, it also could be a histogram. Okay, but relatively speaking, this bar graph or histogram would represent a frequency distribution of a given measured outcome. The normal distribution is basically just a symmetrical distribution, right? A perfectly normal curve would have equal frequencies in a stepwise fashion away from the mean, going both above and below. So in this bell curve, or in this normal curve, we would expect the mean, the median, and the mode, which are all of our measures of central tendency, to be equal to each other. Okay, so the frequencies of the scores are going to deviate from the mean in a predictable pattern. The actual standard deviation might be, various values depending on what you're measuring, but it should be predictable in terms of how the deviation works above and below. Okay. So why do we want data to be normally distributed? The normal distribution, similar to random sampling, is an assumption that's used for all parametric statistical tests. Okay, so when you have ratio or interval data, you have to meet the assumption that you have normally distributed data in order for the results of your tests to be actually accepted and interpreted for what they are. What shape do we assume a population sampling distribution looks like? Normal distribution, right? So if we collect a sample, and if that sample is truly representative of the population, the sample distribution shape should be similar to that of the population distribution shape. So that's why we also want a normal distribution for our sample, because that would be representative of what the population distribution would look like. Okay, statistical inference, we talked about it last week a little bit. We're going to talk about it this week a little bit, and it's simply, right, looking at how generalizable are your results. The more similar our distribution is, or the more similar our sample distribution is to the population distribution, the better our statistical inference is going to be on how a particular intervention might work on a certain group of people. We'll talk about that even more next week. But the last question that we can ask to kind of answer this question is which measures are presented in the distribution, right? And that's our mean and standard deviation. Okay, so remember that the mean is really sensitive to extreme scores. So if we don't have normally distributed data, the mean is going to shift towards that extreme score. Okay, and standard deviation, we also know, could be influenced by extreme scores because we're taking the difference between a raw score and the mean and then adding up, right? Or we square, add all of those up, divide by your sample size minus 1, that type of thing. But in both of these most commonly used measures, right, of both central tendency and variability, they are the most sensitive to extreme scores. So if we have extreme scores, we don't or might not have a normal distribution. So it's important that we have a normal distribution to make sure that our statistical tests run nice and smoothly. As a side note, I wanted to talk about something called the central limit theorem. This states that if a sample is large enough, the sampling distribution of a parameter will be normally distributed. Okay, remember that we reference parameter to population. Okay, so if our sample has enough people in it, when we put that sample, right, or let's say we take a bunch of samples, and we plot all of those samples on a single distribution, the shape of those sample means plotted on that single distribution should be representative of our population. Okay, so usually once you get to a big enough number in your sample, it should be more or less what your population should look like. It doesn't matter if you add more people, your distribution should still assume a normal shape. The actual population may not be normal though, so that's something to consider. We usually assume that it is, which is why we take that assumption on for our statistical tests. But when you take an accumulation of your means, again, from randomly selected samples, that distribution should be normal. Okay, so you might not always think that your population is normal, but the sampling distribution of your population should be normal, which is what we're actually comparing when we look at samples. Okay, does your samples distribution look like the sampling distribution, which is a bunch of randomly selected samples, and their means plotted on a regular distribution? A sample that is large enough is usually determined by running a power analysis, which can be run in tandem with a sample size analysis. Large samples are assumed to be about 30 to 40 subjects. Again, you should probably check this based on the variables you're working with to actually make sure that you've met power. Samples that are not large enough may not need normality testing. So if you've got 30 to 40 subjects, you can relatively assume, based on the central limit theorem, that you likely have a normal distribution. It's always good to check your values anyways, just in case you have an outlier. Maybe you can identify a value that was input incorrectly. But usually if you have enough people, normality isn't really a concern anymore because it should naturally happen. When we're talking about the normal curve, we also have to acknowledge the empirical rule. We saw this curve in our previous portion of this lecture series, but the empirical rule is also called the 68, 95, 99.7 rule, which is a little bit tedious to say. But basically, if you look at this distribution, where 0 is the mean, and then we have +1, +2, +3, and -1, -2, -3 standard deviations from the mean. As you move outwards, between one standard deviation, right, plus or minus 1, we should have about 68% of our data included in that region under the curve. So if we took our frequencies that exist between plus and -1 standard deviations, divided that value by our total sample size, it should be close to about 68%. If we look between plus and -2 standard deviations from the mean, we should have about 95% of our data within that region. And then between plus and -3 standard deviations, we should see about 99.7% of our data. Being outside of plus or -3 standard deviations is very rare. Usually if you have a value that exists in these regions, that would be an outlier. Okay. But you can also look at this by adding up the percentages in each of these regions. So maybe you wanted to know what percentage of, if we have a normal distribution, right, what percentage of individuals would lie 2 standard deviations below the mean. You could add up 13.59 and 34.13 to figure out how many people or what percentage of your scores would exist within -2 standard deviations from the mean. Maybe you wanted to know what percentage of individuals lie between -1 and +2 standard deviations from the mean. Again, you add up the percentages, and that relatively is the number or amount of people in your sample that exists between those 2 standard deviations. This is very similar to how percentiles are calculated, right? So looking at or below a given value tells us what percentage of people in our distribution have a given score or below that score. So I've kind of been commenting on percentages as an area under the curve. We can also refer to values under the curve as a decimal, so a non-percentage value, right? And that decimal number can be anywhere between 0 and 1, similar to percentages which exist between 0 and 100%. and that would express the probability or the likelihood of obtaining a given value or raw score in the distribution given certain bits of information. And those certain bits of information will be the mean, the standard deviation, and the sample size. We can use these 3 bits, right, to say at a given raw score, whatever exists at -1, we compare that to the mean, or the distance from the mean, right, divide by our standard deviation, and we should get the probability that that raw score exists at or below, right, in the distribution. So the area under the curve is very similar to the percentage that we would get if we added all of these up, given that we have a normal distribution, of course. Similarly, we could find how many people exist above a certain value. Okay, so the probability that we are at or above whatever raw score exists at this red line. We can also look at values that exist between. Okay, so I gave you guys examples in the previous slide. Again, the method is basically if you have a normal distribution, you can add up these existing percentages that you know of. But if we've got like this 2.5 situation going on here, a better way that we can estimate the area under the curve, or the probability that a score exists between, above, or below certain regions, is using z-scores. Okay, so standard deviations, remember, tell us how far a value has deviated from the mean. Now, we can express standard deviations in terms of the units that we have gathered for our dependent variable, but you'll also notice, like in the previous slide, we also can represent standard deviations as 1, 2, 3, or -1, -2, -3. These are examples of what we call standard deviation units, meaning it's just 1, 2, or 3, okay? In terms of the actual units, your value might assume something different. So let's say that our mean was 10 and our standard deviation was 5. 10 would exist at the mean, right, in units of what we have measured. 1 standard deviation above that, or 10 plus 5, would be 15, so that would be the raw score that exists at the 1 standard deviation from the mean. We could then add our standard deviation 5 again to get 2 standard deviations from the mean, which would be 15 plus 5, so 2 standard deviations from the mean would be 20. Plus 5, we would get 25, right? If we went below the mean, we're subtracting our standard deviation in the units that we measured. So starting at 10, minus 5 would be 5, minus 5 would be 0, minus 5 would be -5. So I go through a video that kind of explains all of this, but just conceptually knowing, if we're looking at standard deviation units, we can also kind of coincide these with z-scores, or what are known as z-scores. And 1 z-score is equal to 1 standard deviation. So if we're at plus 2 standard deviations from the mean, that is also equal to 2 z-scores. The formula to calculate the formula to calculate z-scores are basically the same for a population or a sample. The only thing that changes are the symbols that are used. For our class, we'll always be working with samples, so we can just go off of this, right? X being a raw score, X bar being the mean of your sample, SD being the standard deviation of your sample. So again, these are the 3 ticket items that you would need to know to calculate a z-score. This is going to help us determine the probability that a value lies, and I loosely use this, less than or equal to a certain raw score of interest. Okay? In other words, it's the area to the left of a given z-score. So if we go back to this slide, calculating a z-score gives us this picture. Right? We have a raw score of interest, and we're given the probability that the value exists at or below the given raw score of interest. Okay, so Less than or equal to, you'll see in the activity why I use this loosely, but for some people it helps to visualize. You just think at or below. So the area from the raw score and to the left. Z-scores are also a type of standard score, so the other type of standard score we've already mentioned so far in the lecture series is our coefficient of variation. So in other words, it doesn't matter what the units are that you've measured, a Z-score is a Z-score. And the Z-scores will be the same for any calculation that you run, regardless of the units that you have collected. Now, to use Z-scores, we have a Z-table. Okay, and it looks something like this. I have a PDF version that is more legible, but just so you get an idea of what the table looks like. We have both a positive Z-score table, which will give us all of the values from the 50th percentile to the 100th percentile, and we have a negative Z-score table that gives us the 50th percentile to the 0th percentile if we're moving down to the left. Okay, which should make sense, right? Because when we plot our distribution, if we have a normal distribution and our mean is in the center, when normal distribution, the mean, the median, and the mode should all be equal to each other. And we know the median is associated with the 50th percentile, or the middle value in the distribution. So that is why we get the 50th percentile down as negative values, or -1, 2, or 3 standard deviations below the mean, and the positive, or +1, +2, +3 standard deviations from the mean as the 50th to 100th percentile. Again, we'll talk about percentiles next week. Just kind of bear with the topic for right now. But just to reiterate, because this is the concept that everyone always forgets, the Z-scores give you the percentile under the curve to the left of the Z-score. Right? That area under the curve, again, represents the probability that you have randomly selected a value at or below than your raw score of interest. So, how do we read the table? When you get a Z-score, you're usually going to calculate it up to 2 decimal places. You notice this first column here lists up to 1 decimal place, or the 10th decimal place. So you'll find your Z-score based on what you've calculated, find where that exists. Let's say we had 1.83. So on my table, I would go to 1.8, and then I would go to the column that has 0.3 as my hundredths place. That value, or all of these values rather, represent the probabilities that a value exists at or below them, the raw score of interest that you've calculated your Z-score for. Right? In other words, the area to the left of the curve. So, again, just to visualize a little bit differently, negative Z-scores, again, are going to be associated with negative standard deviations, okay, and percentiles between 50 and 0. So just so you get associated 0 to -3, right, 50 to relatively 0. Positive side is going to be the area to the left, again, so I have both of these arrows pointing the same direction so that we get it in our heads. We have the area to the left, right? But those are going to be positive Z-scores, or positive standard deviations from 0 to 3, and percentiles associated from 50 to 100%. Okay? I want you to note also we use Z-tables when we're estimating percentiles. Okay? We say they're estimated because we are assuming that the sample data are normally distributed. So when we calculate percentiles in various other ways next week, those ways are going to be exact percentiles because we're using all of the data that we have collected in its rawest form. Estimated percentiles because we're using the mean and standard deviation. Remember that those two calculations are going to be affected by extreme scores. So if you have an outlier either above or below the mean in any of your distribution or data sets that you're working with, that could skew the mean and standard deviation, and if not caught, can affect the estimated percentiles that you calculate. So that's why we say Z-tables give us estimated percentiles, using other methods to calculate percentiles would be methods for exact percentiles. But again, that's next week. I wanted to give you guys practice in the lecture. Okay, so if you need any help calculating or performing this activity here, I have linked a help video in your PowerPoint to YouTube, so you can watch that, and I walk you through all of the steps on how to calculate this. But basically, you're just going to be using the z-score formula on these 3 raw scores, and then you'll use your z-table to estimate percentiles at those given raw scores. I've also included a solutions slide so you can check your answers, especially if you're doing them on your own and you want to see if you got them right. So feel free to practice those as many times as you like. You can also make up different raw scores that might exist in this distribution, and you have more practice. Okay. The next thing I wanted to talk about was constructing a distribution. We will have questions that pertain to constructing a distribution on the exam, so do make sure that you do all of the practice problems for this, because it is a challenging thing that some students just don't really grasp onto. So I've included more practice problems in lecture this semester. I'm hoping that helps. But these are the basic procedures that you would use to construct a distribution. You start by drawing a normal curve, assuming that you have a normal distribution. Okay. You're going to notate where the mean is. So generally speaking, we should put that in the middle. You can either note it as a standard deviation unit, which would be 0, or you can put x bar, or you can put mean, or you can actually put the mean in the units that it's been collected in. In this example, it's VO2. And then from there, you notate plus or minus standard deviations in either the units of measurement or the standard deviation units. So in this case, we can see that our standard deviation is 5. So you can either say 60 plus 5, 65 plus 5, and keep adding 5 as you move to each standard deviation, or you can just stick to 1, 2, and 3, and minus 1, minus 2, minus 3. Doesn't matter. You then locate the position of the raw score of interest within your distribution, which usually I give you the raw score of interest, and then you would shade the appropriate region based on kind of the goal of what you're trying to find. So remember that we can either look at a percentage of values below a raw score, above a raw score, or between 2 raw scores. For our example of values that exist below or lower than a given raw score, let me get a pen, and we'll do red. That's cool. Okay. So the first thing is to draw a normal distribution, and please excuse if this is messy, but I'll try my best. Whee! So normal curve. We then notate where the mean is, so again you can either write 0, you could write x bar, you could say x bar is 21, and write the actual mean. Okay. For this example, we're saying that our dependent variable is the weight in pounds lifted in a bicep curl, and what we want to know is the probability that a person can curl at least 10 pounds. So we have a mean of 21, we have a standard deviation of 6.46, so personal preference, I like making 3 tick marks, 1, 2, and 3, and this is plus 1, plus 2, plus 3 standard deviations. Then you do 3 tick marks. Please excuse my non-straight line, but this is how it goes when you're drawing with a mouse. Okay, and then we have minus 1, minus 2, minus 3 standard deviations. This is totally fine. Or, alternatively, you can take your handy-dandy calculator and you can say 21 plus my standard deviation of 6.46. So 21 plus 6.46 gives us 27.46, and then you would write 27.46. And then taking that number, you would add another 6.46. And then we would get 33.92, right? And then you add 6.46 again. Going down this way, right, you could have 21 minus 6.46, which would give us 14.54. Okay, and then you subtract 6 from that, or 6.46 from this number, you get minus 2 standard deviations in terms of the units you've measured, which would be pounds, right? Minus another 6.46, you kind of get the picture, okay? So you can write in standard deviation units or in the units of the variable. We want to know what the probability is that a person can curl at least 10 pounds. So in the scope of our values here, we can either find where 10 would exist in our distribution, or we can also calculate the z-score. So remember, z is equal to x, which is 10, minus the mean, which is 21, divided by the standard deviation, which is 6.46. So if we calculate this, we get a z-score of negative 1.70. From here, we then can look at our z-table, right, and find an associated probability with negative 1.7. I'm not going to do that just yet because I don't want to X out of my PowerPoint, but you guys know how to look up negative 1.7. I just want to show you how we would look at it in a shaded region. So negative 1.7 is going to be between negative 1 and negative 2 standard deviations. Let's say it exists in a cyan color, and it exists here. Okay, so this is where 10 pounds would exist and or 1.7 negative 1.7 z-scores. We're interested in the probability that a person can curl at least 10 pounds. So that means I'll fix this on your PowerPoint, but this should say at most. I was copying examples, so I'll just fix that now. This should be at most 10 pounds, so meaning they can lift 10 pounds or less, right? Because we're looking at lower than a given raw score. The probability that they can do that would be the area to the left of the z-score. And the z-table is going to give you the probability or the area under the curve to the left of this z-score. Okay? So if we were I asked you, construct a distribution. These would be the steps that you would use to do that, given that we're looking for something under or below the mean. Or not below the mean, below a raw score of interest. Now let's do another example, but instead of looking at values below a certain raw score, we want to look at what's the probability a person can curl more than a certain raw score. So we'll do red pen color again. We have our distribution here. Again, we do 0, plus 1, 2, 3 standard deviations from the mean, and minus 1, minus 2, minus 3 standard deviations from the mean. In this example, we have the same mean and standard deviation. Okay, so we can easily calculate our z-score to find the probability that a person can curl 15 pounds or more. So raw score is 15 minus 21 divided by 6.46. So we should be negative again. 15 minus 21 divided by 6.46 gives us negative 0.008. 0.93. I'll round up. Okay, so in our distribution, 0.93 should exist between 0 and 1. Let's say it exists here. Okay, so that's this guy, and or is also equal to x is 15, which is our raw score here. If we want to know the probability, right, that we have a person who can curl 15 pounds or more, we're describing this region, right? Because as we go up, we get greater pounds or greater weight. Remember that when you look this value up in the z-table, though, the z-table is going to give you this region. Okay? So, again, z-table, when you look this value up in the table, you're going to get this region. However, we want the blue region, right? So, when you're calculating the probability that exists in this blue region, you have to remember to either do 1 minus the probability, let's say P is represented by this area over here. You have to do 1 minus P to get the probability that you're looking for. Whoops, pen color cyan. That will give you your shaded region, which is here. Okay. If you're looking at your probabilities as percentages, you can easily change this to 100 minus the probability as a percentage in the green region, and that will give you this other region, right? Because we can look at our distribution from 0 to 100%. So whatever is in one region is not in the other region. So that's how we can kind of justify. So this isn't a number, it's just the shaded region, right? 1 minus what you get from reading the z-table will give you the probability greater than your raw score. I also wanted to do an example if we're looking at a region between raw scores. So I'll change my color back to red. We'll do our normal distribution. So we have 0, 1, 2, 3, and -1, -2, and -3 standard deviations. Okay. And this time we have, or we want to know the probability that a person can curl between 20 and 25 pounds. This means we need a z-score for 20 and we need a z-score for 25. Okay, so z-score for 20 would be 20 minus 21 divided by 6.46. The z-score for 25 would be 25 minus 21 divided by 6.46. Okay, if we do these in our calculator, we get negative 0.15 and 0.62. Okay, so 1 positive and 1 negative. And I'll do these in different colors, so this one will be cyan. So negative 0.15 is relatively going to be about right here. So that's this guy. Okay. And the probability that we get from our z-table when we look up this value is going to be noted as this region here. Okay. Now I'll change my color to, let's say, magenta. And that will represent my z-score at 25. So we have a 0.62, which is relatively halfway between 0 and 1. Okay, so this is where 0.62 or If we're looking in terms of our units, 25 pounds. When we look at the z-score in the table, the probability that we get from the table is going to be this region. Okay. Now, if we are interested in the probability that exists between 20 and 25, what we have to do is we take the probability of this purple region, and then which is from here all the way down, and we subtract the blue region so that what we're left with is this piece here. Okay, and this is what we get, or this yellow region is going to be the probability between 20 and 25 pounds. Okay, so you take the probability at 25 minus the probability at 20, and you end up with the probability between 20 and 25, which is my yellow shaded region. Okay. So again, you guys can actually look up what these probabilities would be. I have included some other examples with linked videos in your PowerPoint so that you can go through those on your own, actually deal with finding the probabilities using the z-tables a little bit more, but just in a different way than we already have. And then if you click to the following slide, I do give you the solution with the shaded region marked as a red line with an arrow, and the probability that you would have gotten had you used the z-score or the z-table correctly. Okay. If you also reference the notes area of your PowerPoint, I write out the calculation using a z-score formula, what the probability is associated with the z-score that you should have calculated as a percentage, and a probability between 0 and 1. So I'll let you guys do those practice problems on your own. And I want to summarize z-scores as a whole. So again, we can either use them to calculate percentiles, specifically estimated percentiles when we are assuming we have a normal distribution. We can also use them to create confidence intervals, which we will work on in future classes, probably next week. And then we will also use these scores to calculate skewness and kurtosis. So we're bringing it back to distribution shape. Okay. We're never going to get a perfectly normal distribution when we're collecting from samples. However, to make, again, statistical comparisons, we need to show that our data is not markedly skewed or oddly shaped. So you'll notice later when we run certain statistical tests, we run the stats with the assumption that we have a normal distribution, so we must test for normality.